In this video, I'm going to be going over the geochemistry of rhyolites and how we can use geochemistry in exploration to recognize promising sequences of rocks which formed in the juvenile arc or rift environments that we know are so closely tied to high heat flow, as well as voluminous and long-lived hydrothermal systems which mineralize the seafloor, forming our VMS deposits. We will also be going over the patterns we see with economically prospective rhyolites and also why we see those patterns. So why do we care about rhyolites? They tend to be associated with mineralization in many settings, primarily with our bimodal mafic deposits, but also with bimodal felsic and felsic siliciclastic deposits. And this here is a diagram of the bimodal mafic deposit that occurs at Noranda in Quebec, Canada. You can see in red rhyolitic lavas piling up around a vent, producing a mound-shaped structure called a lava dome. And on top of that lava dome is a thin mineralized layer. Why do we see this association between rhyolites and mineralization? So in rift sequences, you get upwelling of the asthenosphere due to the extensional state and decompression melting that's taking place. That upwelling melts the base of the crust, and the first minerals to melt are the felsic ones, your quartz, your case bars, as per Bowen's reaction series, and that same heat source, responsible for partially melting the Earth's crust, is also responsible for driving hydrothermal convection in the near-surface environment. And these felsic rocks, formed by partial melting, have a different geochemical signature than those that are produced by arc magmatism and the hydration melting that occurs there, or by fractionation, where minerals crystallize in response to a cooling magma. These are the different geochemical classifications of rhyolites: F1, F2, F3A, and F3B, and I summarize the characteristics of all these different rhyolites and also whether or not they're associated with mineralization. And we'll be going over each one of these characteristics and describing them in more detail and exactly why F3 rhyolites have these characteristics and are associated with mineralization. The first thing we'll be going over is the calc-alkaline versus tholeiitic trends. And what these are is, as a magma cools, it drops out certain minerals and its composition changes. Depending on if that magma is oxidized or reduced, it will drop out different minerals and follow a different fractionation trend. And how a magma becomes oxidized is via input of subduction zone components. So when the slab subducts, it carries some water with it. When it reaches a sufficient depth, it melts, releasing that water, and that water goes into the mantle wedge, oxidizing the magmas there. Those magmas eventually rise to surface and create our calc-alkaline products. And if we look back, we'll notice that F3 rhyolites associated with the tholeiitic trend have the highest potential to host VMS mineralization. This is because tholeiitic rhyolites tend to occur in the back arc environment where subduction zone components aren't oxidizing the magmas there. So tholeiitic means we're in the back arc, and the back arc is good because we have large-scale crustal structures derived from rifting that allow hydrothermal fluids to circulate, and there are also shallow intrusions capable of driving hydrothermal convection. And these two things tend to be more rare in the arc setting unless it's being rifted. So now we're going to go over the rare earth element patterns we see in prospective rhyolites. Almost all of our rare earth elements are immobile due to their large ionic radius. And what immobile means is they aren't moved around easily by hydrothermal fluids. One exception to this is EU. It's the only three charge rare earth element, and it's quite often used as a vector for hydrothermal alteration in VMS systems. And what we see in terms of rare earth element trends is that uh, weakly fractionated rare earth patterns tend to be associated with the F3 rhyolites, which have the highest potential to host VMS mineralization. And what that means is that less of the rock has crystallized. For example, only 10% of the rock has cooled and crystallized, whereas 90% remains as a liquid. And rare earth element patterns during crystal fractionation, the ratios of them tend to remain relatively constant, unlike partial melting, which we'll discuss later. And this diagram on the right shows the variation in rare earth element trends depending on how fractionated the magma is. And what a less fractionated rare earth element trend indicates is that we have high level magma chambers which are close to surface. I can't explain why this is, but you can go to this Lesher 1986 paper and he explains it in quite a bit of detail, but I have to say it's a bit over my head. And if you can explain it in the comments, feel free to do so. And these high-level magma chambers, these enhance hydrothermal circulation in the near-surface environment. So now we'll be going over NB and TA anomalies and what those tell us about a rhyolite's prospectivity. So NB and TA are incompatible high field strength elements. And what that means, when I say incompatible, it means these elements don't fit into the crystal structure of mantle minerals very easily. Thus, they prefer to be in the melt. And when I say high field strength, what I mean is these elements are immobile, the same as our rare earth elements, although NB and TA are not rare earth elements. They are also not moved around easily by hydrothermal fluids. And why do we choose incompatible high field strength elements to classify rhyolites? This is because a low degree of melt of a mantle rock will have a higher concentration of incompatible elements. This is due to them not being easily incorporated into the crystal structure. So as melting proceeds, the concentration of these incompatible elements will decrease because there will be less of them to enter the melt, and their concentrations will become more diluted as partial melting proceeds and other elements enter the melt. Thus, incompatible elements and their concentrations will decrease with increased percent partial melting, and high percent partial melting typically occurs within the arc. Therefore, within the arc, we typically have negative NBTA anomalies, and weak to absent NBTA anomalies are associated with those F3 prospective rhyolites and are interpreted to not be subduction related, or in other words, formed in the back arc. So to sum things up, if we know the story of the felsic volcanic rocks and where and when they came from, we can deduce whether the environment was a juvenile or developing arc, where rifting and high temperature magmatism existed in the near surface environment and drove hydrothermal venting, mineralizing the near seafloor environment. And this process is different from what we see in the arc or environments where rifting and higher temperature magmatism don't exist, and gives the rocks a unique geochemical signature represented in NBTA anomalies, rare earth element profiles, as well as tholeiitic trends. And this is a little diagram I made. Here's a diagram I created to sum up the thought process you can use when you see a rhyolite and want to understand if that rhyolite might have formed in the same environment, which commonly forms VMS systems. So a rhyolite can either be tholeiitic or calc-alkaline. Tholeiitic products indicate you're in the back arc environment where magmas are reduced. Rhyolites can have either less fractionated rare earth element trends or very fractionated rare earth element trends. The less fractionated trends tend to be associated with shallow intrusions, which are good for hydrothermal circulation. They can have negative TA and B anomalies, which indicate a high percent of partial melt, which occurs in the arc. We don't want this, as we want a low percent of partial melting, as that happens in the back arc environment. And these TA and B anomalies, they're just another proxy for telling us we're in the back arc environment, similar to how we use tholeiitic versus calc-alkaline magmas. Here's some of the resources I used in the creation of this video that you can go to if you want more information about any of these topics, and videos I plan to make in the future. I actually wanted to conclude in this video, but this video is already getting really long, so I decided to cut them out. One being the ideal geotectonic environment for VMS deposits, also Rhyolite Geochemistry specific to the Flin Flon deposits in Manitoba, Canada. I'm also open to other ideas for future videos. If I ever end up making another video, I'm not sure, but I guess we'll see in the future. Until then, bye-bye.